This exercise is a proof exercise. It's actually L'Hopital's rule for complex functions, at least for the 0 over 0 case. There's also an infinity over infinity case. And it goes like this. If we're given f and g complex functions that are differentiable at the point z0, and they satisfy that f and g are both 0 at z0, and an additional condition that g prime is not 0 at z0, then the limit as z goes to z0 of f of z over g of z, which if you just substitute it would be 0 over 0, is actually equal to the derivative of the numerator at z0 over the derivative of the denominator at z0. And I'll mention that this is not identical, though it's similar to the formulation for real functions from Calculus 1 for the 0 over 0 case, and there we used the mean value theorem in the proof, but there is no mean value theorem in the case of complex functions, so we'll do it a bit differently. So now the proof. The limit of, I'm just copying it from here, of f of z over g of z, what we can do is alter the numerator. Because f of z0 is 0 and g of z0 is 0, we haven't changed anything here. Now, we can divide both numerator and denominator by z over z0. Again, we haven't changed anything because we've divided both top and bottom. Now, the limit of a quotient is a quotient of the limits, provided that the denominator doesn't go to 0. So we put the limit over the limit. And what we get is this expression, and I'll explain. The numerator is equal to the derivative of f at z0, because this is precisely the limit for the derivative, and we're told that f is differentiable at z0, so this limit does exist. And similarly, the denominator. We were also told that g is differentiable at z0, so this limit exists too. And furthermore, this is not 0, which justifies breaking the limit of the quotient into the quotient of the limits. So yeah, it's equal to this because what I wrote, f and g are differentiable, and this is not 0. And this is exactly what we had to prove, so we are done.